The first iterative method in determining solutions to systems of linear equations is Gauss Jacobi. Check out the process here in numerical solutions to CE problems. In this video, we will be continuing the iteration of the examples used from the previous video, so the check has already been done. After identifying if the system can be iterated, the variables are extracted, and the first iteration, which we will notate as iteration 0, will be assumed. For discussion, the assumed initial value for variables is 0, but you can also use 1 or other values. Then the iteration is done by plugging values with each step. From the first example we checked previously, we have the equations arranged for x, y, and z. Manipulate terms in each equation to simplify the formula, like x becomes a quarter of the quantity 3 plus y plus z. Y is taken as a sixth of 9 plus 2x minus z. And z is 1 all over 7 of the quantity negative 6 plus x minus y. For iteration, we assume the initial value as 0, starting with x sub 1, which is a quarter of 3, plus y, which is 0, and z, also 0, becomes 0.75. Y sub 1 is also computed as 1/6 of 9 plus twice of 0 minus 0, and that is 1.5. And also, z sub 1 is 1 all over 7 of negative 6 plus 0 minus 0, resulting to negative 0.8571. The second iteration will be solved using the values from the first iterations. So x sub 2 becomes 1/4 of 3 plus 1.5 minus 0.8571, which is 0.9107. Y sub 2 is 1/6 of 9 plus twice of 0.75 minus negative 0.8571, and that gives 1.8929. Then last for this iteration is z sub 2, which is 1/7 of negative 6 plus 0.75 minus 1.5, resulting to negative 0.9643. The third iteration uses values from iteration 2. So x sub 3 is a quarter of 3 plus 1.8929 minus 0.9643 to give 0.9821. Y sub 3 is 1/6 of 9 plus twice of 0.9107 minus negative 0.9643, which results to 1.9643. Then z sub 3 is 1/7 of negative 6 plus 0.9107 less 1.8929, which is negative 0.9975. At this point, although we can see a trend, let's just continue with some more iterations. For the fourth one, x sub 4 is computed as 1/4 of 3 plus 1.9643 minus 0.9975, and that is 0.9917. Y sub 4 is also taken as 1/6 of 9 plus twice of 0.9821 minus negative 0.9975, which is simplified as 1.9936. Then z sub 4 is 1/7 of negative 6 plus 0.9821 minus 1.9643, or negative 0.9975. The fifth iteration can be solved starting with x sub 5 as 1/4 of 3 plus 1.9936 minus 0.9975, giving 0.9990. Y sub 5, on the other hand, is equated as 1/6 of 9 plus twice of 0.9917 less negative 0.9975, or that is 1.9968. Z sub 5 is 1/7 times negative 6 plus 0.9917 minus 1.9936, simplified as negative 1.0003. Continue to the 6th iteration to check if decimals can get even closer. So x sub 6 is 1/4 of 3 plus 1.9968 minus 1.0003, which is 0.9991. Y sub 6 is 1/6 of 9 plus twice of 0.9990 less negative 1.0003, which is 1.9997. Z sub 6 is 1/7 of negative 6 plus 0.9990 minus 1.9968, and that is negative 0.9997. Then, with the 7th iteration, x sub 7 is 1/4 of the quantity 3 plus 1.9997 less 0.9997, which shows 1. Y sub 7 is a 6 of 9 plus twice of 0.9991 minus negative 0.9997 to get 1.9997. Then Z sub 7 is 1 all over 7 times negative 6 plus 0.9991 minus 1.9997, and that is negative 1.0001. Let's have a couple more iterations to verify the values. Proceed to x sub 8, that is 1/4 of 3 plus 1.9997 minus 1.0001, yielding the value of 0.9999. Y sub 8 is 1/6 of 9 plus 2 times 1 minus negative 1.0001, which is 2. Then, Z sub 8 is 1/7 of negative 6 plus 1 minus 1.9997, or negative 1. And if we work on the 9th iteration, x sub 9 is 1/4 times 3 plus 2 minus 1, or that is 1. Y sub 9 is 1/6 times 9 plus twice of 0.9999 minus negative 1, giving 2. And Z sub 9 is 1/7 times negative 6 plus 0.9999 minus 2, which is negative 1. Notice that the values are very close each other, if not the same. So, we can conclude that x is equal to 1, y is 2, and z is negative 1. Take the second example checked for iteration from the previous video. It was found that the system of equations cannot be iterated, and let's see if it is not indeed. So from the first equation, x turns out as 7 minus y minus z. Y is also taken as 1/3 of 13 minus x minus z for the second equation, and z is taken as half of 13 less x minus 2y. And just the same, we assume the initial values of 0. So for the first iteration, we can proceed starting with x sub 1, that is 7 minus 0, which is 7. Y sub 1 is 1/3 of 13 minus 0, giving 4.3333. Then z sub 1 is half of 13 minus 0 minus twice of 0, or 6.5. For the second iteration, x sub 2 is 7 minus 4.4 of 3's minus 6.5, which is negative 3.8333. For y sub 1, we have 1/3 of 13 minus 7 minus 6.5, and that is negative 0.1667. Z sub 2 is 1/2 of 13 minus 7 minus twice of 4.3333, and that is negative 1.3333. At this point, we can notice jumps from our variables values, like from positive to negative. Still, we check if we can come up with specific values. So at x sub 3 equated to 7 minus negative 0.1667 minus negative 1.3333, giving 8.5. Y sub 3 is 1/3 of 13 minus negative 3.8333 minus negative 1.3333, that is 6.0556. Z sub 3 is 1/2 times 13 minus negative 3.8333 minus 2 times negative 0.1667, giving 8.5833. Now we got positive values again. So we proceed with the fourth iteration. X sub 4 is 7 minus 6.0556 minus 8.5833, resulting to negative 7.6389. Y sub 4 is 1/3 times 13 minus 8.5 minus 8.5833, which is equal to negative 1.3611. And Z sub 4 is 1/2 times 13 minus 8.5 minus twice of 6.0556, giving negative 3.8056. Now we can conclude that the values for the system of equations are divergent, and we cannot have a single value for each variable using the iteration method.